So we started the first session in the afternoon. We had 3 talks. The first talk is given by Seok Kim from Seoul National University. The title of his talk is Self-Dual Strings. Welcome, please.
Thank you very much. It's a great pleasure to have my first chance to visit Taiwan. And I'd also like to thank the organizers for giving me a chance to talk about my work. So self-dual strings are unique objects which appear in a special setting, which appear in a special special branch of all six-dimensional conformal field theory. So it's an object which we have to better understand to understand some aspects of six-dimensional CFTs. So I thought about how to introduce it. There are many ways of motivating these strings, and its observables. And today I decided to motivate it from Seidel-Witten theory and instant time. So roughly speaking, the work will be based on the later part of this work, after introduction, will be based on a paper that I posted this summer with Seok Kim at Harvard and Jemo Park at Comstek. And also some later part of my talk will be related to a work in progress with 2 collaborators of mine, and also with Dr. Seok Kim and Kias. And following 2 papers have partly overlapping with our papers. So I'll be dealing with supersymmetric quantum field theories in various dimensions, preserving A supercharges. So let me explain to you the 4-dimensional settings and what are the important observables. So 4-dimensional N equal to 2 gauge theories can come with various gauge groups and various matters and hypermultiple form. And it has a universal branch which we call Coulomb branch, because the 4-dimensional vector multiplet always contains 1 complex scalars to which we can give expectation values. And in this Coulomb branch, the quantum effective action of the Coulomb branch is characterized by 1 complex function called pre-potential, which is a function of the complex scalar. And Seibel-Witten has gave the beautiful Seibel-Witten solution more than 20 years ago about how these pre-potential behaves in the Coulomb branch moduli space. So starting from the very simplest model, which has SU2 gauge group without any matters, for certain classes of theories, they decided the form of this pre-potential, basically using the holomorphicity and some assumptions on the singularity structures in the moduli space. And the features of this pre-potential is that it's a function of the coupling constant of the gauge theory, and it applies non-perturbative, all other non-perturbative contributions from what is called the Yang-Mills instanton. If you consider the Euclidean quantum field theory of flat R4, Yang-Mills instantons of finite actual configuration satisfying this equation characterized by instanton numbers, and it acquires all other contributions. So to microscopically compute these suggested Seibel-Witten solutions, a few years later, Nekrasov has invented a way of computing the pre-potentials by his Nekrasov's instanton partition functions. So it's a partition function of the gauge theory, acquiring all other instanton contributions in a specially deformed flat space background called omega background. And if we compute the full Nekrasov partition function and take a special limit, the leading coefficients in which we take the deformation parameter to be 0 is the pre-potential. Okay? So this is the way Nekrasov suggested to microscopically derive the Seibel-Witten solution of N-equal-2 gauge theories. Okay? And if you consider the form of Nekrasov partition function in the instanton number expansion, the coefficients, the k instanton contribution of the partition function can be computed from what is called the ADHM matrix model for k instantons. So ADHM matrix models are consisting of certain matrix-like data. For k instantons, it consists of k by k, and for your, let's say, SUN gauge group, it has some rectangular matrices as well. So these data, subject to certain constraints, are labeled parameterizing the instanton moduli space. So the k instanton contribution of the partition functions are given by suitable matrix intervals of this ADHM matrix data. So the simplest case with SU2 without any matters that Seibel-Witten originally considered has the matrix degrees of freedom characterized by this Kuiper diagram. You can go up to higher dimension. This becomes a 5-dimensional supersymmetric gauge theory preserving minimal supercharges. So it's 5 gaining in 1 theory. And the same problem exists if you consider this 5-dimensional theory compactified in a circle. Okay? So the four-dimensional effective action is again characterized by free potential, but the difference is that in the Coulomb branch, the free potential acquires this time from the contribution from the infinite power of Kaluza-Klein modes on S1. And this is actually the setting in which Nekrasov started to study his problem of computing the Nekrasov, formulating and computing the set partition function for free potential. Because this five-dimensional uplift of the four-dimensional problem has many robust and solid features using which he could formulate this problem well. This is because of the fact that if you interpret this S1 factor as the Euclidean thermal circle, with periodic boundary conditions, you can interpret this k instanton contribution of the partition function in 5 dimensions as the Witten index of the k instanton particles. Okay? So the self-dual configurations in 4 dimensions can be uplifted to stationary particle configuration in 5 dimensions. So it's a BPS Witten index which computes the spectrum of k instanton states bound to certain charged particles in the Coulomb branch. Okay? And this kind of partition function, this time, is computed by the quantum mechanical uplift of the matrix models, where you give time dependence, basically the circle coordinate, to all the matrix degrees that I explained to you in the previous slide. By doing this computation and reducing down to small circle, you can go back to the 4-dimensional size of Witten problem I explained to you. But this 5-dimensional version of this instanton partition function is also interesting in its own right if you have an interest in studying 5-dimensional quantum field theories. So 5-dimensional super Yang-Mills theories are by itself ill-defined theories because 5-dimensional gauge theories are non-renormalizable. But if you consider the 5-dimensional gauge theories, which have some consistent UV fixed points, for instance, which are having 5-dimensional supercomponent fixed points, you can use this instanton partition function to study the spectrum of certain BPS particles in, let's say, 5-dimensional quantum field theories. It's again related to 6-dimensional supercomponent field theories in a bit more indirect way. Again, as I told you, the partition function can be computed from this time the path integral of a supersymmetric ADHN quantum mechanics model. So this has been very well known for a long time ago, more than 10 years ago. Now, just blindly, one can consider going one higher dimension because Yang-Mills theory preserving A supercharges can be defined up to 6 space-time dimensions. You can imagine that, you might naively imagine that this is a boring extension of the exercise to one higher dimension without too much physical motivation, but that turns out to be wrong. I'll try to explain the physical meaning of this one higher dimensional uplift of Nekrasov's study in later transparencies in the context of 6-dimensional supercomponent field theory. But before doing that, I'd like to first explain to you that this one higher dimensional uplift is suddenly becoming extremely subtle in contrast to the 4 and 5-dimensional settings. This is because of the fact that 6-dimensional theories with A supercharges suddenly turn out to be chiral. Okay? So 4-dimensional n equal 2 theories are non-chiral, but 6-dimensional minimal supersymmetry has 1, 0 chiral supercharge. So it suddenly tries to turn out to be a chiral supersymmetry gauge theory. Okay? And in chiral theories, especially since it's a gauge theory, you have to worry about chiral gauge anomalies. So you first have to make your 6-dimensional gauge theory well-defined before studying the Nekrasov partition function problem. The problem, again, will be a partition function of 6-dimensional gauge theory compactified on a torus, where this time the instanton configuration can be uplifted to 1 plus 1 dimensional strings. So it will be instanton strings partition function compactified with it. But before that, let me try to make the theory well-defined, meaning free of gauge anomalies. So in order to make this chiral gauge anomalies cancelling in this theory, it turns out that one has to couple this supersymmetric vector multiplet into what is called a tensor multiplet. So for simplicity in this program, let me consider the case in which the Yang-Mills theory's gauge group is simple, and it couples to one tensor multiplet. Okay? So tensor multiplet field has one scalar and one two-form potential fields whose three-form field strengths are constrained to be self-dual, and it has some formulas. And the way the anomaly is cancelled by coupling vectors into tensors is as follows. So one can write down the following action, which couples the tensor multiplet fields, I'm showing the code one part, with the vector multiplet fields, And the structure is such that the expectation value of the tensor multiplex scalar is giving rise to the inverse of the Yang-Mills-Stock function. And if you look at this supersymmetric action, especially the bosonic part of it, this action suffers from classical gauge anomalies. If you make a suitable gauge transformation of B and F, the variation of the classical action is non-zero. And the way that the anomaly cancellation is achieved is that this classical anomaly is cancelled against one-loop anomalies caused by the gauge-Eno fields in the vector multiplex. So this is called the Green-Schwarz mechanism. So the six-dimensional 1-0 theories, in most cases, are made anomaly-free by this anomaly, the Green-Schwarz mechanism. And these classical and one-loop anomalies are cancelling only for special choices of gauge groups. Technically speaking, it has to be to do with the fact that the quartic Casimirs are not existing as an independent operator. But for simplicity, for the cases without matters and only with vector and tensor multiplex, this Green-Schwarz mechanism works for only this small number of gauge groups. So if you restrict your interest to simple gauge groups. So it starts from SU2, SU3, SO8, and all the other exceptional gauge groups. This is the consistency requirement for local anomaly cancellation for gauge symmetry. And this system has to satisfy a further constraint to be free of what is called the Witten's global anomaly in 6 dimensions. So in the path integral, there could be some large gauge transformation which might potentially make the path integral measure ill-defined. And requiring that to be cancelling gives some further constraints for certain gauge groups. So for instance, for SU2, SU3, and G2, the system is made consistent, free of global anomalies, only when there are a particular number of charged hypermultiplet matters. Okay? So for instance, for G2 and SU2, the simplest kind of theory without any matters are made inconsistent by this global anomaly. The number of hypermultiplets is never allowed to be zero. So after considering all these certainties, one arrives at a little bit surprising conclusion that what used to be the simplest Yang-Mills theory in 4 and 5 dimensions, with SU2 without any matters, is totally inconsistent. So this is a kind of very surprising 6-dimensional certainty. And in a sense, the simplest Yang-Mills theory in 6 dimensions comes with SU3 gauge group, in the sense I explained. Is there any questions so far? Now let me try to explain to you what is the physical reason one might be interested in this kind of 6-dimensional gauge theories and their partition functions. Also in 6 dimension, Yang-Mills theories are non-renormalizable. So whenever we consider it, we should make sure that it is embedded into a consistent quantum theory. Okay? So again, we consider the cases in which these 6-dimensional Yang-Mills theories are having a consistent UV fixed point. Normally, we study this consistent UV conformal field theories from string theory engineering. And from various approaches, one has studied the 6-dimensional superconformal field theories, and in recent years, people have arrived at what is called the atomic classifications. So basically, you have some atomic building blocks of conformal field theories, and these are forming the kind of simplest set of conformal field theories, using which you can form a more complicated and richer class of CFTs. So the atomic CFTs can be roughly classified in the following table. So there are a few numbers of them which have the following simple gauge groups. So these are exactly the kind of gauge groups I listed here, which are also free of global anomalies. So I get rid of SU2, G2, and the rest is just in this table. There are some exceptional cases which doesn't have any gauge symmetry at all, just have a tensor multiplet. And there are some more exotic atoms which have product gauge groups, which cannot be decomposed into each other. So once you have this finite number of atoms, the way of forming a more richer class of 6-dimensional conformal field theories can be done in 2 ways. First of all, you make quivers of these gauge theories. Yes?
In the product gauge groups, the written global anomaly cancels between the 2 gauges?
Yes. So G2 times, let's say, SU2, they are having some half hypermultiplexes with bifundamental matters. The number of bifundamental is precisely the way that the global anomaly cancellation is fulfilled. More examples. Yes. So the way of making more complicated quantum field theories is firstly to make quivers. according to special rules, you form a, let's say, a linear quiver of these gauge theories, introducing more, let's say, a kind of bi-fundamental matters between them. This is a one way of making a more richer class of six-dimensional CFTs. And another way of making a richer class of CFTs, which will be used for later, is to add hypermultiplet matters and making the gauge groups larger, so that it's related to the original theory by Higgsing. Okay? So we call this unhiggsing procedure, by adding matters and enlarging the gauge group. These are the two ways in which you can make a more richer class of conformal field theories. And as you see, this SU3 atom is in some sense one of the simplest atoms. So using that, you can consider a large class of superconformal field theories. And the way that six-dimensional Yang-Mills theories is related to these CFTs is that it provides an effective quantum field theory description in what is called a tensor branch. As I told you, this is an action of tensor vector coupling system. We give an expectation value to scalars, which sets up the Yang-Mills coupling scale. So this effective action is reliable unless the energy scale of one's interest is not larger than this inverse coupling scale. So this is the way supersymmetric Yang-Mills theory in six dimension is related to more consistent microscopic theory. Now let me explain what self-pure fields mean. So in the six-dimensional theory, so if you consider 4 or 5-dimensional quantum field theory, let's say in the Coulomb branch, you find lots of interesting particle spectra. Okay? So for instance, if you go to Coulomb branch, breaking the gauge symmetry into this abelian part, you find W bosons, okay? Massive W bosons, whose masses are proportional to the scalar expectation value. You also find monopoles, you also find diodes, you find many kinds of massive particles. But if you go to the tensor branch of six-dimensional theory, the analogous object is no longer particles, but the strings. They are tensionful strings whose tensions are proportional to the tensor multiplet scalar expectation value. And we call these self-dual strings. We call these self-dual strings because the tensor field in the tensor multiplet were forced to satisfy the self-duality constraints, so the notion of electric and magnetic charges, distinction of no electric and magnetic charges disappear. So the notion of W bosons, monopoles, diodes, all collapse down to what is called the self-dual strings, having equal electric and magnetic charges under this twofold potential. Okay? So a typical example of these self-dual strings, if you're familiar with string and M theory, are the following things. The most famous six-dimensional conformal field theory are engineered on the coincident multiple M5 planes. And going to tensor branch means that you separate these M5 planes. And these string-like objects, self-dual string in this context, are nothing but the open M2 branes suspended between these separated M5 branes so that they make a string-like locus on 6 dimensions. So these are self-dual strings, which sometimes M strings. There are many other engineerings of 6-dimensional CFTs, let's say preserving 1-0 supersymmetries. If you allow these M5 branes to probe certain kind of singularities in M theory, it's kind of orbifold fixed point in what is called the heterotic M theory, supporting EA symmetry. And if you allow these M2 branes to be suspended between this orbifold fixed point and the 5 branes, you get what is called the E string in the 6-dimensional CFT, sometimes called E string theory. And these self-dual strings in the tensor branch are playing very important roles, similar to these massive objects in the Coulomb branch of low-dimensional gauge theory. And its partition function has been playing important roles in understanding certain aspects of 6-dimensional CFTs recently. If I have time at the end of my talk, I'll talk about some future directions on how to use these self-dual strings for more exciting studies of 6D CFTs. And the reason why vectors of partition functions are important is exactly because the instanton strings in the Yang-Mills theory description are self-dual strings. If you remember the bosonic part of the action I wrote you, it has the following typical characteristic coupling. So it gives rise to a B mu nu chart. So the self-dual strings are nothing but the string-like objects which couple minimally to this B mu nu tensor field. But if you have Yang-Mills instanton string solitude in Yang-Mills theory, it has non-zero FHF charge, so it naturally provides the self-dual string charge. So in this 6-dimensional Yang-Mills effective description, instanton strings are self-dual strings. And necros of partition functions are nothing but the partition functions of self-dual strings wrapped in the torus. So the Seiberg-Witten theory in necros of calculus uplifted to 6th dimension certainly acquires a slightly new meaning.
Sorry, does the gauge field couple with B?
Huh?
Is A coupled with B?
Yeah.
What is F?
Yeah. F is the field strength of the gauge field A.
No, what is F?
What is F? F is F.
Yeah,
It is F. It's the field strength of gauge field A.
Does it depend on B?
Huh? F is that.
So how does A couple with B?
How is A coupled with B? A coupling with B.
Yeah, does it?
Like this. F depends on A this way, and it coupled with B according to this Lagrange. So if you have non-trivial Yang-Mills instanton, you have non-zero FHF, and that source is B mu nu, and it's becoming the self-dual string.
Well, I thought A is twisted by B, but it's not.
A is not, A and B are independent fields. A and B are independent. Other questions? Yeah. No, it's not from non-abelian F5. So this effective action is valid only in the what is called the tensor branch, and tensor branches are now obtained whenever you give expectation values to tensor multiplet scalars. So whatever the non-abelian tensor multiplet is, many of them become massive in the tensor branch, and you are left with a bunch of abelian tensor multiplets. So even if you consider the non-abelian tensor theory, if you separate these M5s, you're only left with light abelian tensor multiplets. So we're studying a special corner of this six-dimensional series, which surprisingly become relevant even if you are interested in certain kinds of conformal phase observations, like superconformal and so on.
So B is a super partner of the scalar which measures the relative.
That's right. Yeah. So yeah, these are the super partner division. So from now on, hoping that the motivation is sufficiently given for the study of six-dimensional necros of partition function on R4 times C2, I try to explain to you how to compute that. The way we compute that is just trying to mimic what people have done in 4 and 5 space-time dimensions. Because in 4 space-time dimension, necros of partition functions are computed from the ADHM matrix models, at least for some simple gauge groups like SU2 or SU3. In 5 dimension, it was computed by the path integral of the ADHM type matrix quantum mechanics. So we can try something similar. You promote all these ADHM matrix model data to 2-dimensional quantum fields. And by studying this worldsheet supersymmetries, at least in the infrared, you know that it should be preserving 2-dimensional 0,4 superconformal field theory. So on the worldsheet of self-dual strings, we have 0,2 superconformal field theory. And ADHM gauge theory, ADHM quantum field theory also takes the form of the gauge theory. So it should be regarded really as a UV quantum field theory after RG flow flowing to this infrared conformal field theory. Okay? Because ADHM gauge theory has always a dimension for coupling constant.
So the infrared description should be a nonlinear sigma model.
Nonlinear sigma model, but it's very incomplete. You know, instanton sigma model has target space which has singularities, so it's an incomplete system. It always have to be replaced by a UV complete description. Let's say this is GLS and partition. And the partition functions of these 2-dimensional quantum field theories, let's say for K instanton strings or K self-dual strings, are giving the coefficients of the 6-dimensional necros of partition function. So whenever now I say 6-dimensional necros of instanton partition function, I understand it as the partition function of this 2-dimensional quantum field theory on a torus, preserving certain number of supersymmetries as dictated by necros of set. Okay. So this two-dimensional gauge theory, quantum field theory, from which we can try to compute this network partition function, one can naively think it's a two-dimensional uplift of ADHM matrix model. So as I said, SU2 is a wrong, inconsistent model, so you consider the next simplest thing SU3. And considering this SU3 example, we'll show another surprising certainty, which is quite common in all kinds of circular strings. So what you do is you consider the SU3 ADHM gauge theory in living in 1 + 1 dimension, now having the rectangular matrix and the adjoint matrix as well as a superparticle. But you suddenly realize that in 2 worldsheet dimension, this ADHM quantum field theory again becomes inconsistent. Because I told you it's a chiral theory on worldsheet, so we should start worrying about this worldsheet anomaly of this UK gauge symmetry. So on the world volume of K instantons, the ADHM quantum gauge theory says that UK gauge symmetry to be present, but it turns out that the naive ADHM period is just anomalous. Okay? So it fails to provide a good description. Okay? So the naive application of these lower dimensional techniques seem to fail. So how can we proceed from this? The way I found to be successful is to cure this bad quantum field theory, and you can cure it in various ways. But basically, the strategy is to add more fields. Firstly, in a way that the gauge anomalies are canceling, and you have to carefully add the fields that many of the physics that we require, many of the physics that we already know about circular strings are successfully reproduced by these good UV descriptions. So there are many strong constraints because we indirectly know in various approaches, 6-dimensional Yang-Mills approach or string theory engineering, many properties of this quantum field theory, although we don't know any systematic description. So I'm going to find a systematic 2-dimensional quantum field theory description, which I think satisfies all the experimental constraints that we know about these strings, and then using this systematic approach, we can compute lots of other observations. Okay? So this is a bit a complicated story. So initially we try to preserve the full 0,4 supersymmetry when you try to find a UV gauge theory. But that kind of attempt often fails, because when you try to find a UV uplift of infrared conformal field theory, it often partly breaks the symmetry preserved by the infrared. Sometimes the global symmetries of the conformal field theory are broken in the UV theory. And sometimes it's often happening that the supersymmetries are not completely preserved in the UV theory. So the theory that the cure of the SU3 ADHM gauge theory that we'll find only preserves a fraction of this 0,4 supersymmetry. Okay? And the matter contents that we have to add are taking the form of the superfields in the 0,2 subsymmetry of 0,4. And in the 0,2 symmetry, you can add what's called a chiral multiplex, suitably charged in SU3 and UK, and some Fermi multiplex. Okay? You won't have to know what this 0,2 multiplex will mean, but after judiciously inserting certain multiplex, you find that the SUK and the overall UR gauge anomalies are completely cancelling. Of course, there are more ways of rendering gauge anomaly cancellations, but as I'll explain to you, there are further very strong constraints that will immediately tell you that random additions of anomaly cancelling multiplex won't do the right physics. So this is just one kind of choice of addition of extra multiplex that renders gauge anomaly cancellation.
Yes. This problem of the anomaly is present also for the other theories which are not SU3?
Most of them.
Understanding
many of them. I mean, in some kind of choice, with some choices of gauge groups, we luckily have naive ADHM quantum mechanics working well, but it's not guaranteed.
I see. And this, let's call it exercise, tell you also how to treat the other cases?
No.
It's case by case.
It's always case by case. It's always case by case because of following. As you may see, most of the gauge groups are exceptional. And in those cases, we don't really know what kind of ADHM description to start from. So we only have a kind of ansatz for UV uplift for classical gauge groups. But what I'm going to say is that for classical gauge groups, that ansatz may work or may require some modification.
I see.
But as I tell you, if you understand SU3, you can understand some closely related gauge group like E2s or SO7. Because these three gauge groups are all related to each other by Higgs's.
I see.
But not everything.
I see.
Okay. So this may be a very dirty addition, but it has been chosen by very delicate consideration, which I'll explain to you. So since we had added lots of extra fields, you might be worrying that it may give rise to lots of wrong physics. Because if you add lots of other fields, the infrared moduli space completely changes if you don't carefully think about the potentials and so on. So normally if you add more scalars, your moduli space at low energy may become larger. So you should have to introduce careful potential terms to all these extra fields so that the SU3 instant of moduli space is not changed in the infrared. That's another very difficult constraint, which cannot be fulfilled by arbitrary insertions of anomaly cancelling matters. And that requires us to add a very judicious superpotential to lift all the extra scalar moduli space. And that is possible with only this kind of additions of matter, as far as we could say. And let me explain to you how this kind of correct moduli space appears.
Do they form 0.4 hypermathematically much?
Sorry?
So do they form 0.4 much?
This one. Yeah, this one. No. That's why I say that UV theory has reduced supersymmetries.
Okay.
But we have some signals of the infrared supersymmetry enhancement to 0.4. But in the UV, for the matter content, you only have 0.2. If you start to turn on interaction, which gives right physics, it's scaling 0.1. So let me try to you what kind of moduli space we get, assuming that we add suitable superpotential, which is in our paper. So let me explain to you one consistency check of this model. So firstly, we study the classical moduli space, meaning that we study the configurations of scalars, the original radiation fields, and other fields are added. And you study the algebraic configuration, which satisfies this bosonic potential to be vanishing. Okay? And we find two branches of solutions. For simplicity, we just did the exercise for single instantons. Because for multi-instantons, it's a notorious fact that the algebraic zero potential conditions, or the ADHM constraints, cannot be exactly solved. So at least for k equals to 1, you get a very interesting kind of structure. Because the potential being 0 yields two branches of solutions, classically, which meets at a point. So the first branch is producing exactly the SU3 instanton moduli space that we want, because if you carefully investigate the vanishing condition of this potential, in the first branch, extra fields are all required to be 0, or massive, while the remaining original ADHM fields are required to satisfy these algebraic equations, which are known as the ADHM constraints. Okay? So the original ADHM data satisfying these constraints are known to yield the correct SU3 instanton moduli space. Even after you do the one-loop integration out of these massive matters, you find that the moduli space metric of SU3 instantons are not changed in the first branch. Okay? And this correct SU3 instanton moduli space is taking the form of hyperkähler cone, which is closely related to the nonlinear sigma model having 0.4 supersymmetry. So this we find to be a very strong indication that infrared 0.4 supersymmetry enhancement is happening. If you integrate out these extra massive fields. The complication is that we turn out to find the second branch by solving this equation of motion, which meet with the original branch only at a single point. Technically, we call it a small instanton singularity, where physics become complicated. Okay? But if you carefully investigate with the potential I mentioned to you, the one-loop integration out effect for the massive fields, it turns out that the second branch is subject to some one-loop quantum correction for the equation determining this vacant ground state condition. So after the quantum correction, we find a signal that the second branch is detached from the first branch, contrary to the classical picture. Okay? And this mechanism has been suggested by these people in the context of 0.2 gauge linear sequence. So we conjecture it as an exact property, quantum property, that the first branch doesn't acquire quantum correction, while second branch does and detaches quantum mechanically from the first branch. If this happens, it means that the UV quantum field theory will be flowing at least to two decoupled infrared decoupling sectors of quantum field theories, and the first branch of conformal field theory is what we are interested in. just to comment, because related to what Dario asked to me, this nonlinear sigma model is incomplete because a moduli space it has curvature singularity at the origin when the instanton size becomes smaller. So this nonlinear sigma model, it fails to provide a complete quantum field theory description. It always has to be complete by a, let's say, UV complete gauge theory that I given to you. And all the other fields that I explained to you becomes massive away from the singularity, but they secretly provide massless degrees of freedom only at the small instanton field, telling us how to UV complete this nonlinear sigma.
But this UV completion could be understood as giving a blow up of the singularity somehow, or no? No.
No, it's not.
Okay.
It's not. Yeah, I mean,
Probably the singularity just gets corrected because of this.
I see. Okay.
yeah. If you approach the singularity, the higher curvature corrections and the loop corrections become important, so you lose control of
I
this
see.
quantum field. So this was a basic check that the quantum field theory I explained to you is giving rise to correct basic physics. Now I can explain to you much more subtle physics by studying Nekrasov partition function. It's a partition function of 6-dimensional theory and R4 times T2, and you can understand it as the 2-dimensional gauge theory's quantum torus partition function. We call it elliptic genus. It's a torus partition function of quantum field theory preserving certain supersymmetries. And too much detail, but just suffice it to say that you can decorate this partition function with lots of chemical potential parameters for the symmetries that commute with the supercharges that we use to define the elliptic genus in Nekrasov partition function. Okay. So it's kind of supersymmetric torus partition function. And in the case the quantum field theory is a gauge theory, these gentlemen some years ago have computed the supersymmetric path integral of the gauge theory on the torus and have shown that the elliptic genus reduces down to a finite dimensional contour integral. Okay? This rule is not very complicated, but it simply gives you the result of the, as a result of the computation, elliptic genus being given as a sum of particular resids of this contour integral. Okay? The rule is very complicated, but if we apply this rule to our gauge theory, we get a simple, the following closed form expression for the resids, which is again complicated, but you don't really need to understand the details of this to get my story. And the resids are classified by so-called Young diagrams in particular way, which has been appeared in the previous literatures of instanton calculus. But anyway, we are having closed forms for the elliptic genus for any instanton number. So I'm gonna explain some physics about it, which is I think is quite subtle and surprising. I basically explain two physics with this elliptic genus, Nekrasov partition function. One is that I deformed my theory by adding lots of other extra fields compared to the original ADHN quantum theory, okay, because of gauge anomaly reasons. But if you compactify the 2-dimensional quantum field theory in a small circle, you're going to get a gauge theory description of instanton particles in 5-dimensional gauge quantum field theory. Okay? And for describing instanton particles in 5-dimensional quantum field theory, original SU3 ADHN quantum mechanics is completely fine because there's no issue on gauge anomaly. So we have two apparently very different quantum mechanical description of 5-dimensional instanton particles. And you may ask whether the 1-dimensional reduction of this elliptic genus is agreeing with the traditionally computed Nekrasov partition function. And the 1-dimensional limit can be taken by replacing all these theta functions by sine functions, which has to be the one-loop determinant of quantum mechanics on a circle. And each sine function or theta function reflects the matter contents of the field. So if you look at the individual resid expressions, the partition function computed from traditional SU3 ADHN quantum mechanics and our one may look extremely different. But one can show that by using lots of trigonometric identities that apparently different expressions are completely equivalent to each other, only in 1 dimension. Okay? So one can understand that our SU3 quantum field theory is providing our UK gauge theory are providing an alternative ADHN-like formalism if applied to supersymmetric quantum mechanics for instanton particles. But our alternative and dirty ADHN-like formalism is the only one which admits a 2-dimensional uplift, contrary to the traditionally used ones. So this provides a very strong consistency check of our theory. And for later consideration, let me explain to you the simplest case where the string number is 1. And then this formula, dirty formula, reduces down to something reasonably simple, where its free 1, 2, 3s are the SU3 chemical functions. Okay, so if you study this network of partition function, on the one side you can really get a convincing test that we got a consistent description, and building upon this confidence, you can certainly change your logic and use our systematic approach to make powerful predictions on the 6-dimensional CFTs and string theory. Let me explain to you firstly how we could test our theories. So, as a final test, as another test of our theory at k equals to 1 that I explained to you, one can show that one can first note that some coefficients of this elliptic genus partition function has been computed by a totally different method. And that has been done by these gentlemen by using the topological string amplitude calculus techniques. And the rough reason why topological string calculus becomes relevant is the following. So if you try to realize the corresponding 6-dimensional quantum field theory, SU3 component field theory in string theory, one normally takes the SF theory engineering, which is the type 2B string theory with space-time dependent axial dilatons. So if you put this type 2B or F theory on elliptically fibered Calabi-Yau, you can engineer various kinds of 6-dimensional CFTs. And the particular Calabi-Yau can be used to engineer the following SU3 quantum field theories that I explained to you. And if you do the topological calculus, string calculus on the corresponding elliptic Calabi-Yau, you can extract out some coefficients of this elliptic genus partition function. After you expand the partition function or free energy in a particular chemical potential. So these are expansion in what is called omega background parameters, or more precise, or alternatively, the angular momentum chemical potential. So in the string, topological string language, we call this the genus expansion, the genus of topological string worldsheets. And if you focus on what is called the genus zero contribution, which is straightforwardly obtained from our elliptic genus, some coefficients of this genus zero partition function are computed from the topological string methods if we make a further expansion of this quantity in the SU3 fugacities, SU3 and the elliptic genus's momentum fugacities. So depending on these three quantum numbers, momentum and SU3's Cartan charges, these black numbers are the degeneracies computed from these topological string methods. But from our method, we can get it immediately by expanding our theta functions in the fugacity. And they completely agree with each other. So one can get convinced at this stage that we got the correct description. And it's easy to generalize it in our approach because these people have to compute every number one by one by doing some hard computation using computer. But we just expand our result forever and just we keep getting the corresponding DPS degeneracies of these self-zero strings. Okay? So on one side, we can test our theory strongly with existing data. On the other hand, our calculations are giving the all-order sum exact form of the topological string amplitude on certain Calabi-Yau, which should be providing certain non-perturbative completions of topological string observables. So it should be very meaningful in that setting as well. One could do some further checks having to do with anomaly polynomial things, but let me skip this part. Final application that I explained to you related to other self-zero strings with different gauge groups that was asked by somebody. I explained to you that for SU3 gauge theory, a single example, we have found a kind of alternative radiation-like description which is valid in 2 dimensions and also in 1 dimension. But once you have this alternative radiation-like description, surprisingly it turns out that you can recycle it to get a more interesting class of instanton string counting or self-zero string countings. So this is related to the fact that SU3 superconformal field theory in 6 dimension is related to other gauge theories related by Higgsings and unhiggsings. So note the following fact that SU3 can be unmixed in a particular way given as follows. So you start from this SON theories with various methods and spinors and fundamental representation. They can be Higgs by following the sequence ending on this non-Higgsable SU3 theory. You can also start from the exceptional gauge theories and Higgs it to reach this SU3 theory that I explained to you. And always at the end of the 16 sequence, right beyond SU3, you have G2 gauge theory in 6 dimension with one fundamental matters, or SO7 gauge theories in 6 dimension with 2 matters and spinor representations. You may be interested in studying the self-zero strings of these theories, but apparently they look very difficult because G2 instantons and SO7 instantons with matters and spinor representations are precisely the cases